So what I want to talk about is how we are storing STL containers on NVM. And I don't want to promise too much. We're not storing them completely consistently. We're just doing what we need for our database. And I'll explain what I mean by that in a second. Things that I'll cover. First, I'll talk about what type of data we see in in-memory databases. So we're looking at it from the perspective of database developers, and especially how write-once data is more important than generally perceived by the NVM community. Second thing is the main part showing how we can use PMR and representation-aware containers to implement STL on NVM. And then I'll give a short performance evaluation. Okay, so my background is we're developing HiRise, which is a research database, relational in-memory, hybrid transactional and analytic, open source, and using C++. We're looking into different research areas. So it's not only an NVM research database. We have people looking into self-driving databases, replication, footprint reduction, and so on. And this is important because it means that I'm actually the only one who's interested in NVM, and the other people don't want to be bothered by it. If you want a comparison, what we're doing in HiRise is most similar to what SAP is doing in HANA. Okay, so what do we have in in-memory databases? I tried to put down a couple of data structures on two axes. First one being the horizontal axis, where on the left we have all the data that are called base data. That's all the data that we need after a restart. All that's the reason why we have a database, because we want it to be there even if we restart the system. On the right we have scratch data, which is completely useless after we restarted the system because all the SQL connections are gone anyway. And then on the vertical axis, on the bottom we have data that is rarely read and, more importantly, rarely written. And on the top we have data that is heavily accessed with many writes. So I hit some slides about this. If there is anyone who wants to talk about data structures on databases in more detail, we can do that in the break. Just to summarize it, so when we started, we looked into the top left area, and we thought that was the original value proposition for NVM, especially for databases, meaning that we have persistency that is closer to CPUs, we have super fast recovery, but it soon turned out that we also would get performance hits for random accesses. So things like dynamic indexes or hot table data that is modified consistently, is too slow if we put it completely on NVM. So we put that idea of having a database that is completely on NVM that doesn't use any traditional DRAM anymore aside. On the top right, we have all the things that are traditionally DRAM and that we don't expect to change anytime soon. So when you have a join, for instance, the hash maps that you build for the join are worthless once you restart the database. They are accessed in a random manner. So there's nothing to gain there from NVM except for very big joins. So if you have a join with hundreds of millions of rows on both sides, then you might want to spill it over to NVM and at least move part of your hash map to NVM, get it back later, and that way you can do bigger joins and you don't affect the rest of your system as much because you're using too much DRAM. Okay, so the things that I want to talk about today, though, are on the bottom left. That's data that is important after restart. That is data that is not written as much. Most importantly, we have cold data, cold table data that has been there for a while, that is still being accessed, but that is not being modified too much. We also have things like the result cache. So we cache results from previous SQL transactions, and we can reuse them, and that way we can speed up the execution. Here, the value proposition of NVM that we see is that we get higher capacity and lower cost than DRAM, while at the same time having lower performance impact than we would have with SSDs. And also, if we put everything there on NVM and we flush it properly, we can increase the speed of the recovery. So the goals that we had was to modify our code base in a way where we could benefit from NVM, both from the capacity and from the persistence aspects, but we want to minimize the changes that we need. So we don't want to go all through the code base, introduce NVM data structures everywhere, and force everyone to work with NVM. In the long term, that would probably be a good thing, but I would get people who are working on different things to hate me. So we wanted to use data structures that we already had, make them NVM aware, and we have some limitations that make that easier. First thing, as I've shown on the bottom left, we actually have data that is written only once. Reason for that being mostly that we're using an insert-only model, multi-version concurrency control, where new data is only appended at the end of the table, and then old data is invalidated but never replaced or overwritten. And the second thing is we don't have to care about atomic rights there. So if we compress parts of our table, if we do a merge, if we write that data, then the only thing we are interested in is writing it completely. If we get interrupted in between, we just have to restore the data from somewhere else. So we don't have to deal with all the fences and all the problems that you might see in other data structures. Okay, so I have to do a couple of disclaimers because that topic already came up yesterday. The first thing is, so we are casting memory that has been introduced somehow into the process, into objects, and that's undefined behavior in C++, but it works, so that's not too bad. The problem is if you recompile your program, if you use a different STL, or if anything happens that we haven't seen yet, then it might break. Good thing about that, yeah.
Are you talking about like placement new in the first part? Is that what you're using to cast memory that came from somewhere else?
No, so if you call placement new, you would actually call the constructor as well. What we are doing is, and I'll give you some code examples in a couple of minutes. We have memory where we have an already constructed object, and we just take that void pointer, cast it to a pointer of our object, and we use it as if we already constructed that object. But for some reason, the C++ standard says, if my process didn't create it, it's as good as if it was never created, and it's undefined behavior, and I can do whatever I want.
That's not entirely true.
Okay.
Like, there's now introduced like libcopyable and pod types using query, as you know. It's not, if you have virtual pointers or you get static data,
Right.
for some bit types you can do it.
Okay. I will admit that I'm not completely familiar with all the kinks of that part of the standard, so forgive me if there's something missing there. Good thing here is, so we will need to do some more work if that was about to be used in a product, working out all those STL problems, but since we are researchers, we just hand that off to the product people. Okay, I want to give a short code example. So we have a really simple in-memory table here. We have 3 rows, we have 2 columns. One column is a double column, and then we have an int column, and that's basically what we're working on. And what we want to do is we want to build an immutable inverted index on that, with the value being that double. The position is the offset into that table. So our inverted index in this case is an STD map from a value to a position. We iterate over the table, and we emplace all the entries in the table. Any questions about that one? All right. Now what happens if we want to store that on NVM? If we have a data structure that is completely immutable, the index is also immutable, so it's created, it will never be updated. How can we get that on NVM? So Intel has libpmem object and libpmem object ++, and while the second one doesn't have any data structures for that, the first one has a red-black tree being the implementation that we also have in the STL. So instead of using STD map, we could just use the RB tree from that library. All right, what's the problem with that? That being a C library, it looks like this, and we also had the discussion yesterday that the C code for those things is not quite easy to read, and we would have to replace a lot of things. So everywhere where we use an STD map, we now have to introduce a wrapper to that data structure. That data structure only supports int keys, and most importantly, it gives us more consistency guarantees as we need than we need, because we only write our data once. All right, what else can we do? Can we just give our STD map an allocator and have that allocator allocate memory on NVM? So we create an NVM allocator. I left out some parts here, but the most important thing being the allocate method over here. We again use libpmem object. We make a persistent pointer, and then we define our inverted index as being an STD map just using this NVM allocator. I think the problems should be well known to people who have already built NVM data structures. First one, when we write data to that map, it's not being flushed. Second one, if we have a crash, then we have a persistent leak. Third one, now we introduce that NVM allocator, which is all over the place, and we didn't want to taint our code base with that. And the fourth one, if we restart our process, the remapping will invalidate all the pointers. Okay, so how do we fix all of those? Starting with the first one, that the data is not flushed. What we did was we modified the allocator to keep track of all the allocations that it did in a persistent vector. So libpmem object++ does have a persistent vector, and we simply emplace all the pointers with their length into that vector. That has some cost, of course, depending on the data structure. If you do a lot of small allocations, then that will cost you. But as we will see soon, the cost of that is not as big as the cost of having an actual NVM data structure. Good thing is, now that we have that vector with all the allocations, we can introduce a persist method into the allocator that simply iterates over all the allocations that we've made. We call persist on those pointers, and that way we can be sure that it has been written out to NVM. If instead of storing the void pointer there, we use the object IDs. We can also use the vector that we've written to free all the data that has not been persisted once we restart our process. So we do have that persistent vector, and if we restart our process, we see that persist has not been called successfully. We can simply iterate over all the allocations that we've done in the past, deallocate them, and we don't have any persistence leaks. So that problem is solved as well. Third one, we don't want to have the NVM allocator all over the place. So we want to use one data structure for everything, no matter if it's DRAM or NVM, and we don't want people to have to deal with that. Especially because we want indexes to be able to be stored on DRAM and NVM. Reason for that being that we're looking into NVM as another tier for those data structures, and while the DRAM capacity for indexes may be limited and you don't want to create too many indexes on DRAM, if you have higher capacity on NVM, you might be able to create indexes that were cost prohibitive before. Okay, so the way we solve that is something called persistent polymorphic memory resources. Polymorphic memory resources or polymorphic allocator being a concept in the standard library where you actually type erase the type of your allocator and hide it in a polymorphic allocator. So you use a virtual method call to find out which allocator you're actually internally using, and through that indirection, you call allocate either on DRAM or on NVM. In that NVM memory resource, we can now hold the information about the non-volatile memory pools. And the good thing here is that PMR is not only useful for that, we also use it for our NUMA allocator. So it's already been there, and we don't actually need to change any data structures.
Back to that first slide about C, not C++ standard. There's some things you can't. Okay.
So best thing I can say about that right now is it works. So I've tried it with different versions of Pi, where Pi and ASLR, and so things were all over the place, and I never had a problem. That's definitely not good enough to ship it out and sell it to people, but it's good enough for our research purposes. Okay, so I'm going to skip this. Question was, what can we store in the container? Cool thing about PMR is that PMR also propagates to internal types. So if instead of having double as the value, we have a string, and that string also uses a polymorphic allocator, then PMR guarantees that our outer layer allocator is also given to the inner types, and that way our string is also allocated on non-volatile memory, and it will remain, or it will be persisted when we call the persist method on the allocator, because it got its memory from that allocator. All right, last open problem, remapping invalidates pointers. How can we deal with that? So I mentioned that we tried it out with position-independent code, and if you don't do any modifications, this will certainly crash when you try it. Reason for that is, of course, the STD map uses pointers internally to reference other nodes. If we have strings there, the pointer into the heap is also a regular pointer, and we will never get those pointers to be NVM aware. There's one more thing that comes into play here that helps us a lot with that. That's something that someone gave the name of fancy pointers or representation awareness. And that's something where you can tell the STL containers what type of pointers they should use internally. So instead of using T star, you could, for instance, give them a smart pointer, unique pointer, whatever. This is being used in IPC. So Boost has an offset pointer where the pointer does not store the absolute address, but the pointer stores the address relative to the current address. So we're putting that into our polymorphic allocator. It's a simple thing, so you just have to type def the names pointer and const pointer, and by adding those traits to the allocator, the STL containers automatically use those pointer types and store all those pointers relative, not absolute anymore, and that way you can read your index after remapping it. You might wonder, okay, why don't we use the persistent pointer that comes with PMM object? Reason for that is that we want our polymorphic allocator to be used both for DRAM and NVM, and if we had the persistent pointer there, we couldn't use it for DRAM anymore. Okay, there's another limitation to that. This currently only works in libc++. The libstdc++ does not use those fancy pointers internally. So there was an issue that has been opened in 2016, and there's been a discussion that you might be able to put it into the STL, but it would break the ABI. And so people currently are not too keen on getting that in. So right now it's only working with libc++, unfortunately. Okay, short evaluation. So I mentioned that PMM object has this red-black tree implemented. So that's what we're comparing us against to. This is the red line on the bottom, and then on the very top, we have the STL baseline, meaning a classic STD map on DRAM. So we add all the things that I've talked about, and we're looking into what the performance implications of that are. First one, we add polymorphic memory resources. So this gives us step 2, and as you can see, there is almost no performance impact of that. Third one, adding the offset pointers, relative addressing instead of absolute addressing. That doesn't change too much either. The fourth one is an example where we put everything on non-volatile memory. Without looking into persistency. The way we did that was by using libmemkind. So the difference between 3 and 4 is the cost of actually writing it to NVM without all the flashes. Then we allocate the memory on non-volatile memory, but we don't add that tracking step that I talked about. That's the difference from 4 to 5 that I've labeled potential for new allocators. So everything in between there is the cost of the persistent allocator, in this case, the persistent allocator that came with PMDK. Step 5 to 6 is we add the tracking in the allocator. We don't persist it yet. So that is the cost that I've talked about before. Keeping that vector certainly has a cost, and it's significant. But when you compare it to the cost of the fully persisted tree, it's not as bad. And then finally, when we come to 6, that's the orange line. To 7, that's the orange line. That's the whole thing, where we also call persist on the allocator, and we now have our tree persisted on non-volatile memory. Okay, read accesses are not as surprising. So if we look at the first line, that's again the STL benchmark, second line being the PMR allocator and the offset pointers, we don't really see any difference there. When we go to NVM using libmemkind, non-persistent NVM, then we see approximately 50% cost. If we use our approach, then we are for some reason slower than the non-persistent NVM version. I can't explain that because we use CLWB, so we don't trash our caches. I would expect it to be the same, but I haven't found out what the difference is there. And then if we look into the difference between our approach and the RB tree implemented as part of PMDK, we see that that one is more than twice as expensive even for reads, which is kind of surprising to me. So I'm not sure where that overhead comes from because they don't have to do any persistency work there. But I talked to Piotr yesterday, and he said that there was more of an example. So the RB tree is probably not the most efficient data structure that they have. I just chose it as an example because it mimics the implementation that they're using for the STL as well. Couple of things that I did not cover. The example just used a single memory pool. We do want to use multiple pools so that we can migrate one pool from NVM to DRAM depending on the access characteristics and back. The question there is, how many pools do you want? If you have a lot of pools, then you're flexible in terms of your migration, but you run into fragmentation issues. And then what I will be happy about to talk about in the lunch break is how we integrate that into Highrise, or what we're planning to do, where we migrate things from DRAM to NVM and back, and how that fits into the whole recovery model. Okay, I'm gonna skip that. Summary being that if you want to NVM, you don't necessarily have to look into fully persistent data structures if you only write your data once. Sometimes you can use simpler implementations and you don't have to change your code base as much. I showed how we can use PMR and offset pointers to do so, performance being dominated here by the NVM allocations. And again, the disclaimer, first one, this is lib C++ only. So if you know anyone from lib std C++, yeah.
I know somebody who's working on the low-level I/O library, and WG21, I believe, is the committee that's involved in that, and they've agreed that we have to do something. You can't just say it's illegal. It's not. That's not the right name. If you don't change the bits, and you don't change the compiler, and you don't change anything else, then you should be able to cast, and it should be legal to do that. And if you can't do that, you've got a big problem that they have to do something with that. And they've agreed that they're looking into actually standardizing the low-level stuff so you can do memory maps and it'll work according to the language which currently is undefined behavior to say this is this object. So they know they have to fix this.
That's good to hear. Okay, so that concludes my talk. I'm not sure. I don't think we have too much time for questions, but I'll be around and I'll be happy to talk about this work and NVM and databases in general. Thank you.